Okay, guys, this is Worm from Worm's Maths Academy. Just trying to clear up a few things before the exam tomorrow. This seems to be a really common occurrence. Whoever's writing the exam seems to enjoy this idea. Basically, if I've got an original function and an inverse function, there's a connection between the gradients, and we're about to see what that connection is. So here we've got all of this information. F of 3 is 7, f of 7 is 8, f dash of 3 is 2, f dash of 7 is 3. G is a differentiable function. G is the inverse of f of x. They've done that so that they can write g dash of x easily. We want to find g dash of 7. Okay. Before we do that, if we had g of 7, so if we substitute x as 7 into our inverse function, we would have the point 7 something. We don't know what that something is. We don't really care. Okay, so we've got g of 7 is 7 something. But then if we bring it back to the original function, we know that when we've got an inverse and an original function, when you have an inverse, f of x versus f of inverse of x, if I had 3, 7, that would become the point 7, 3. If I had 4, 2, that would become the point 2, 4, because an inverse function by definition, you switch your x and y values. So from there, we know if I want to find g of 7, if x was 7 in my inverse function, then in my original function, y has to be 7, because they've swapped when we've gone to an inverse. Now we know that our y value is 7. Here our y value is 7. That means that our x value must be 3. So we can see what the gradient is when x is equal to 3. So f dash of 3 is equal to 1/2. Oops, sorry, not 1/2, it's 2. It's written there. But that means that g dash of 7 is the reciprocal of that. So it is 1 on 2. Okay, so if you've got f dash of, so let me just, I'll run this down for you. So we know that the answer here is going to be 1/2. But if I said to you, if I've got the point A, B, if we know that f of A is equal to B, we know that f inverse of B is equal to A, because B, A. We know that f dash of A, whatever that is, let's say it's M, then f inverse dash of B is equal to 1 on M. So whatever my A value is here, I need my Y value because that becomes my X value on my inverse. And then if we evaluate it at the Y value for our original function in the inverse function, our gradient is 1 on M versus M. So it's the reciprocal of the graph at that same, at the opposite Y value, X and Y value switch. Okay, let's have a look at this graphically. So let's go out here. I'm going to clear everything. Let's think of a function that we know. We know x minus 1, let's go plus 1, squared minus 2. Define that. Now its inverse is going to be x plus 2 square rooted minus 1. If you need to work it out, like if you don't know how I work that out, I just did it in my head. But if I let that equal y, change that to a y, change that to an x, solve for y, then it will give me my inverse function. Now we're going to use the top half of the graph. I'm going to define that, just this bit here. I'm going to define that as g of x, which is my inverse function. Don't need that. Okay, so now if we go in f of x, g of x, sketch them both, we only want this for x is greater than or equal to, what was it, -1? Let's have a look. Okay, so there's our graphs. Now, if I said to you when x equals here, when x equals -1, let's have a look at what the gradient of that graph is, the red graph. So analysis, sketch, tangent. Let's go to the other graph and say it's -1. So there's my tangent, hit enter. My gradient is a half, right? So that's when x equals -1. So that means on the other graph, when x equals 0, because we switch out x and y values, on the blue graph, if I sketch a tangent, and this time I put it where I switch the x and y values, I put it when x equals 0, and then if I hit enter, our gradient is 2x. Okay, now, it doesn't matter where you do it, it's always going to be the same thing. So let's have a look now. I will clear this. How do we clear this off? Just hit sketch. Okay, so now let's look at the gradient when x equals 2 on the red graph. So sketch tangent when x equals 2 on the red graph. Okay, we get a quarter. Now that's the point 2, 1. So that means if I go to 1 on the other graph, if I switch the x and y value, if I go to 1 on the other graph, if this is a quarter, the gradient on the other graph should be 4. So analysis, sketch, tangent. Not 1. I wanted a 1. It should be 4. Hit enter. There we are. Our gradient is 4. Okay, so that's a pretty cool property in that if you sketch the original function, sketch the gradient function, switch the x and y values, find the gradient of the first graph at x, use that y value and find the gradient of the inverse function at that y value, the gradients are going to be the reciprocal of each other. For special kids, I guess it's kind of like if dy dx is equal to 5, dx dy is equal to 1 on 5, the reciprocal, because we're looking at the rate of change of x with respect to y as opposed to y with respect to x. Now, in last year's exam, this property was really, really helpful. What I'll quickly do is go through the last question again, and then that'll allow you to see how it works. So, 2000, I wonder if I've got it right here. 2017. Methods. That's Northern Hemisphere. No, that's Northern Hemisphere. Methods exam. Northern Hemisphere. Methods SAC. Methods exam 2 Northern Hemisphere. That's really annoying. Not there. Not there. Methods exam 1. Stuff it. Okay, so here, methods exam 2. Okay, so the last question. Okay, so here we've got the graph of 2 to the x plus 1 minus 2. Part of the graph is shown below. The transformation that maps the graph of 2 to the x onto the graph of f. So if we look at this, f of x plus 1 is translated left 1 unit, and then minus 2 is f of x minus 2. That's translated down 2 units. Okay, so if it's moved 1 to the left, c is negative 1, and if it's moved down 2, d is equal to negative 2. Find the rule and domain for the inverse function of f. Okay, so let y equal f of x. I mean, it's worth 2 marks. I'm assuming it's going to be just the answers, but so if I swap x and y, let's say that. Swap fx and x. So we get x is equal 2 to the fx plus 1, fx plus 1 minus 2, f inverse x. So f inverse of x is therefore x plus 2 divided by 2 minus 1. So x plus 2 log 2 of x plus 2, because bring that across, it becomes x plus 2. Then log 2 it, and then subtract 1. Now, if our domain of this one is all real values, but our range is negative 2 to infinity, well, then our range of this is going to be negative 2 to infinity, but it won't be equal to. Okay, find the area bounded by the graphs of f and f inverse. Okay, so when we graph them, there's going to be a small area, but we want to see where they intersect. Okay, so let's get rid of that. Okay, go back to our functions. So I've got 2 to the power of x plus 1 minus 2. That's my f of x. And then let's say our inverse function is log 2 of x plus 2. And then minus 1. That's g of x. Okay, we want to see where they intersect. So let them be equal. Get rid of that space. Solve for x. More solutions may exist. Okay. So, what the hell? Okay. Playing funny buggers. Let f of x equal f inverse of x. Therefore, x equals negative 1, 0. The area is negative 1 to 0 of the higher graph, which is f inverse of x minus the lower graph, f of x dx, which is, now it doesn't say give a decimal answer, so negative 1, 0, f inverse of x, in this case, is g of x, minus f of x, our original graph, dx. So it's negative 2 on log e2 plus 3, log e2 plus 3. That's our area. Now let's just make it positive. Make sure it's positive to make sure that we didn't stuff it up. Plus 3. Give me a decimal. Just change it to decimal. Okay, so it's positive, but it's really small. And that makes sense. Okay, parts of the graph are shown. So that's the area that we just found in there. The gradient of f and the gradient of f inverse of x at O. So we want to find the gradient of this thing here. Find the gradient of f and the gradient of f inverse of x. Okay, so I'm going to clear all this. So d dx of our original function, f of x, given x equals 0. Okay, I get 2 log e2. So f dash of 0 is 2 log e2. And f inverse dash of 0, it's going to be 1 on 2 log e2, because we know they've got the same x and y value, so that it's going to be 1 on it. But let's just prove me right. 1 on 2 log e2, because when x equals 0, I've got 0, 0 on my original and 0, 0 on my inverse. So the gradients are going to have the property of being 1 is the reciprocal of the other. Okay, the functions gk, where k is an element of all real positive numbers, are defined with g of k is 2e to the kx. Find the value of k such that g of k is equal to f of x. So f of x is that. So let's say g of k, g of x is 2e to the kx minus 2. So get rid of our 2e to the, where's k? K, was it 2kx? 2e to the kx minus 2, k times x minus 2. Define it as g of x, because we'll write over the old one. Okay, now, if they're the same, we'll say g of x equals f of x. Interactive advanced solve, and if we solve for k, don't want to solve for x, I just want to solve for k, because I want to know what k is. That's the translation that's occurred to go from one to the other, which is log e2. So k equals log e2. That's how we change. So if I made that transformation to that graph, I would end up with, if we transformed this graph by making k equal log e2, I'll show you. G of log e2 is 2e to log e2 times x, that's my x out the front instead of at the end, minus 2. I can bring my x up as a power. E to the log e cancels out, so I get 2 times 2 to the x minus 2. But we also know we can add the powers, so I get 2 to the x plus 1 minus 2, and that should be exactly what we have for f of x. But we let our cas do the hard work for us. Okay, find the rule for the inverse function of g of k, where k is an element of real numbers. So g inverse k of x. Now we know what g is. Well, k must equal 42 somehow. Edit, let's copy and delete them all. Okay, so g of x is that. We let that equal x and change the x to a y and then solve for y. So that gives us our inverse function. 1 on k log e, 1 on k log e. Now I'm going to put it over a common denominator, x plus 2 on 2. It doesn't find the rule for the inverse functions. Should say inverse function. There's not multiples. We know x plus 2 has to be greater than 0, so therefore x has to be greater than negative 2. So I'd do that just in case. It doesn't say to state the domain, but I'm going to state it. Okay, describe the function that maps the graph of g of 1 onto the graph of g of k. So, what is g of 1? So in this case here, g of that given k equals 1. Okay, we get 2e to the x minus 2. So g of 1 of x is what the hell is it? When I put 1 into that, I get 2e to the x minus 2, and then g of kx is 2e to the kx minus 2. So we've said g of kx, which is a dilation factor 1 on k, because it's the reciprocal, from the y-axis. That's when it's inside the bracket, like when you're replacing x with kx, that's g of kx. So the dilation factor is from the y-axis and it's on the reciprocal. Describe the inverse. Okay, so if I put 1 into this, we get g inverse of x to g inverse k of x. So I've just got the normal function, and that goes to 1 on k times the same function. So that's a dilation 1 on k from the y-axis. Okay, so we've got pretty much nearly everything answered now except for this. The lines L1 and L2 are tangents at the origin of the graphs g of k and g inverse of k, respectively. Find the values of k for which the angle between L1 and L2 is 30 degrees. So we know, let's get the gradients. G dash of 0. So if I do that in my CAS, what am I doing? D dx of g of x given x equals 0. So I get 2k. Now we know when x equals 0, y equals 0. So g inverse dash of 0 is going to be 1 on 2k. They're the reciprocal of each other. Now, there's a nice thing when you have reciprocals. If I said, we know that our gradient, which is these two things, we know that m equals tan theta. So if I said my angles here, theta, and if I said, we'll say 2k over 1. Because we know our gradient's 2k, so if I said tan theta is equal to 2k, because tan theta is opposite over adjacent. If we look here, if I said that was 90, that's not 90, 90 minus theta, then our inverse, sorry, if we find tan of 90 minus theta, that's going to equal opposite over adjacent, which is 1 on 2k. What does that mean? It means that these two angles will always add up to 90 degrees, which means that these two, tan of these two gradients, tan of theta, if I find tan of theta one and tan of theta the other, they're complementary angles. They'll add to they'll add to 90 degrees. Now, what's the significance of this? It says it wants the angle between them to be 30 degrees. So, if this one, let's change colors. If this one has an angle of 60, then this one will have an angle of 30. Whereas if this one has an angle of 30, then the other one's going to have an angle of 60. Either way, when one's 60 and one's 30, or the other one's 60 and the other one's 30, the angle between those two lines is going to be 30 degrees. So let me show you this graphically. I've got 1 on 2k times x, and I've got 2k times x. Now, so there's my graphs. Let's make, so here, you can see there, when k equals 1, the red graph is higher than the blue graph. When k equals 2, the red graph's higher. But if we go, let's change our values. I'm going to go from -5 to 5, and I'm going to make my step 0.25 and start with -5. So let's just see what occurs as we change this value. So here, as it gets larger and larger and larger, now, the angle between the blue and the red, that could be 30 degrees, but then as we increase k, now the angle could be 30 degrees, and red is bigger than blue. So the first one, tan theta, would equal, or whatever that angle is, that angle there would be 30 with the red line. And then here the angle would be 60 with the red line. So let's say, let's only worry about when the gradient is 2k. Sorry to rub this out, but I need to make room. So let's say m is equal to 2k. We also know that m is equal to tan theta. So there's going to be two cases where the angle between L1 and L2 is equal to 30 degrees. If theta is equal to 30, we get 2k is equal to tan of 30, which we know 1 to root 3. Tan of 30 is 1 on root 3. So 2k is equal to 1 on root 3. So therefore, k is equal to 1 on 2 root 3, which is root 3 on 6. So that's one case. The other case is if 2k, the gradient of the line that has a gradient of 2k, if that's equal to tan 60. Because if that's equal to tan 60, the other graph is going to be tan 30, so the angle between them will be 30 degrees because of this here, where they are complementary angles. So if 2k equals tan of 60, tan of 60 is root 3. So 2k equals root 3. So k is equal to root 3 on 2. Is that right? Tan of 60, 1, 2, root 3. Yep. Okay, so there are two solutions for when k is equal to, when the angle between those two graphs, if it's root 3 on 6 and root 3 on 2, if k is either of those values, in this case here, one of them will be an angle of 60 degrees with the x-axis and the other will be 30, so the angle between is 30 degrees. Likewise, that'll be 30, the first one, and the other one will be 60, so the angle between them will be 30 degrees. Okay, so the complementary property occurs with the gradients because of the symmetry of a triangle and tan of an angle being opposite over adjacent, and then tan of the other angle, the complementary angle, being opposite over adjacent. The property between them is if you have a gradient like 2k, and then you have another gradient of 1 on 2k, the angle produced by that gradient and the angle produced by that gradient together, if you add those angles together, they'll equal 90 degrees, complementary. Okay, now how does that work here? It says find the value of k for which g of k of x and g inverse of x, k of x, has only one solution. Find the value of p. So p is the value for k. Now, if you think about it, when the angle between them was 0, there's only going to be one tangent. How can we graph this? So if I do g of x And if I do, have I got it defined as f of x? I hope I have. And then graph them. Oh, for some reason it plays funny buggers. So given k. Okay, so we've got g of x. Stupid thing. I want to go to here. So what's g of x? G of x is that. And then that's the inverse. We'll just copy that and go in and graph it. Okay, you can see here k is equal to 0.5 when it's 0.75. When k is equal to 0, not when it's equal to 0, when k is equal to a half, they're just touching. Now that comes because they've got exactly the same gradient at the point 0. So we know that 1 of 2k is equal to 2k, i.e. same gradient at 0. So therefore, 4k squared is equal to 1. K is equal to plus or minus 1 on 2, because I've divided that 4 across, then square root it. However, k is greater than 0, so therefore p is equal to a half. So when p equals a half, that's the value of k for which there's only one solution. Okay, let a of k be the area surrounded by the graphs of g of k and g of k inverse. K is greater than p, so k has to be greater than a half. If k equals a half, there's no boundary, but if we make k equal 0.75, we're talking about, zoom in, we're talking about this little area that's produced between the red and the blue graph. Now, as k increases, you can see here it's saying state the smallest value of b such that the area is less than some value, and that value is the value we want to find. So here, what's that area there? We don't know, but we could work it out. But as we increase k, what's going to happen to that area? See how it gets more and more square? So let's say k can go up to, I don't know, 100. I'm going to autoplay it so you can see what happens. So as k finally goes above a half, as it gets bigger and bigger and bigger, look what's happening. That's slowly producing in that area from -2 to -2 to 0 to -2, -2. That's going to produce a box in there. So that area is approaching a square, and that square has a side length of 2. So a of k is less than 4 as k approaches infinity. Therefore, we know that b is equal to 4. So when b is equal to 4, this function will always be less than 4, because even if you use a really big value of k, you can see it approaches it, but it never actually gets to being a perfect square. I mean, we could try an even bigger value, like 10,000, and then move it right up. You can see, still not quite a square, but it's approaching it. Okay, so that's how you work out those types of questions where they ask you, was it on this? No, must have been another one. Where they ask you to find the gradient of the inverse function given the original function. Don't worry about Shahid, that's one of the kids in my class. His other name's Shivam. Shout out to Shivam. This is when I help him with questions, I do it in this thing called Shahid. Okay, guys, good luck on the exam tomorrow. Hopefully this has helped you out. Hopefully they do something like this on the exam so you can kick its ass, and Nossel students, we can put Jelly back in his place. All right, guys. Bye, guys.